I think we've decided as a group, just to reiterate, that we're not having a third exam. We're just going to have the final, so yay. Are your interests and my interests align in this situation? So we're going to talk about addition and elimination reactions today, a little bit about carbonyl chemistry, a little bit about the E1CB mechanism. There's a ton of stuff in this chapter, but I think we'll go in depth on fewer topics, and then if you need to know more about specific elimination reactions, you can always come back to the text. So we talked about the Berge-Dunitz angle and how there's this idea that you need the right trajectory to attack the pi star of a carbonyl. Nucleophiles tend to approach from this angle. And that's going to be important in just a little bit, but we're going to take a step back and just consider simple additions to carbonyl compounds using concepts that we developed in the chapter on kinetics. So carbonyl addition reactions, we'll think about hydration, and whatever we say for hydration could be true for acetal formation. This is the reaction where you add water and you get the carbonyl hydrate, or the gem diol as it's sometimes called. And the reaction tends to be general acid catalyzed, meaning that the protonation happens in the rate determining step. Though specific acid, where you protonate first and then the slow step, specific acid happens too at really low pH. And the basic issue as for a general acid catalysis, let me just draw out a proposed mechanism for general acid catalyzed carbonyl hydration. The idea is that water attacks at the same time as the carbonyl gets protonated by the acid. And you can rationalize this in a few different ways, but the idea is water's not a good enough nucleophile to attack the carbonyl directly. There would be a forward rate constant and a reverse rate constant, and we're going to say that this forward rate constant at least is slow, and so the protonation happens in the rate determining step. You get this intermediate positively charged oxonium ion, which then in a second fast step, and it could be A- or water, removes the proton from the positively charged oxygen, and you end up with your hydrate and your regenerated acid, or H3O plus and A minus. Okay? Now, whether or not you can do general acid catalysis, because the acid's involved in the rate determining step, the acid matters, and you basically need an acid that is good enough to protonate a negatively charged oxygen, so that you don't ever form that, right? So that you would get instead this. So the acid's got to be good enough to deliver a proton to the oxygen in this sort of tetrahedral intermediate, but it's got to be not good enough to protonate a carbonyl compound to generate this oxonium ion. So you're looking for, if you think about this proton and that proton, you're looking for acids whose pKa's are somewhere in the range between 16 and like -2. And so, I mean, this is kind of a nice framework. I remember when I teach carbonyl chemistry in the introductory class, there's always this issue of who attacks first and who gets protonated first and how can you tell. And this is basically it. If you're using an acid catalyst that has a pKa in this range, likely you have to do it under general acid catalysis. If your acid is good enough to protonate a carbonyl, why then you can do that first, and then the slow step is nucleophilic addition. And this can be, what we say here is likely true for a lot of mechanisms that involve addition to carbonyls. Yeah?
Is it faster to in that second method there where you show the carbonyl oxygen getting protonated before the nucleophilic attack, or is it not really that?
You mean here?
Yeah, would that
Okay.
be faster?
Not necessarily, because the idea here is your acid is strong enough. The slow step is nucleophilic attack. So if your acid is strong enough to protonate the carbonyl, that's going to happen first. You'll go to a specific acid catalyzed mechanism where that just happens before and it's a pre-equilibrium, and then you have the slow step. Yeah. All right. So this kind of thing would be true for acetal formation, and we'll see a similar mechanism when we talk about imine formation. Just a set of data to give you a sense for the aspects of carbonyls that make them electrophilic versus nucleophilic. I'm going to show you an equilibrium constant that is basically the equilibrium between hydrate and a carbonyl compound. We'll call this K of hydration. That's the equilibrium constant. And we'll just show you some numbers. The precise numbers aren't important, but the lessons you can learn about reactivity of carbonyl compounds are pretty useful. So the equilibrium constant is 10 to the third for formaldehyde. If you add a methyl group, it becomes 1, or about 50-50. So you could rationalize that how? A couple different possible explanations. Go ahead.
The carbon that you just added will be able to donate some of its electron density to that positively charged carbonyl carbon.
Right. Methyl is an inductive electron donating group. We've also seen where the methyl pi type group orbitals can mix with carbonyl type things, and in the case of valence bond theory, we call that hyperconjugation. So also the inductive effect refers to the fact that sp2 carbons are more electronegative than sp3 carbons. So you've got that. Another potential reason is just is steric clashes, I think, in the product versus the starting material. Presumably in the carbonyl, the bond angles are all 120 degrees, but in the tetrahedral intermediate, they're closer to tetrahedral. That's a tighter angle. They're closer together. So you could imagine that steric hindrance could be a problem in the more alkyl groups you add. So there's both steric and electronic factors. Here's a example that illustrates the importance of electronic factors. We're putting an electron withdrawing group on the alpha carbon, and suddenly we jump up back even higher than we were when we started, right? So that suggests that you can reverse the effect of the methyl group by adding a chloro. So you can use electron withdrawing groups nearby to increase the electrophilicity of the carbonyl compound. If we go to, let's say, the full ketone and compare that to the aldehyde, it's 2 times 10 to the minus 3. So this is 1,000 times, the ketone is 1,000 times less reactive than the aldehyde. And we don't often think about that because we deal with them in the same set of, when we're learning about carbonyl chemistry, we deal with aldehydes and ketones interchangeably, but there is a fairly dramatic difference in reactivity. You can bump up the reactivity of the ketone if you add alpha electron withdrawing groups. In this case, they're adding 2, so we can't necessarily do a direct comparison, but that brings the compensates at least, brings you back up to the area of reactivity of this aldehyde over there. So yeah, the importance of electron donating versus withdrawing groups nearby is key. Another issue is you can kind of use hydration as a way to investigate the impact of strain and ring structure. So the equilibrium constant for butanone is 1. Okay, so the comparison you want to make is with the ketone. It's 1,000 times more reactive than acetone. Presumably, again, compare the hydrated structure to the starting material structure. What do you think is the big difference there?
Taking them out of the plane that the other 2 carbons are in.
Right. You know that in a flat square, the angles have to be 90, right? And you've just made it so that these 3 carbons have to be in the same plane to accommodate this carbonyl, or you have to allow for yourself to not have optimal carbonyl geometry. So yeah, so basically, yes, you want, ideally this bond angle should be 120 degrees, and now it has to be somewhere close to 90. If you go tetrahedral, now the difference between tetrahedral and 90 is less than the difference between tetrahedral and, between trigonal planar and 90. So you relieve some strain and that presumably compensates for the fact that the alkyl group should be electron donating. As you make ring strain less of an issue, you sort of go back to being a same old, sort of go back to being a regular ketone. So cyclopentanone is 10 to the minus 2. Interestingly, cyclohexanone is almost 10 times more reactive than cyclopentanone. And this is kind of an interesting story that you can rationalize with a chair structure. So I'm going to draw cyclopentanone in a chair conformation. Here's the carbonyl group. And if we were to look down this bond between the carbonyl carbon and the alpha carbon, we would see that the oxygen and the hydrogen are nearly eclipsed. The difference, the dihedral angle between them is around 4 degrees. And that introduces, basically you can estimate 4 kilocalories per mole of destabilization. Okay? In contrast, if you go to the hydrated species, you're going to introduce some 1,3 diaxial interactions. But we can estimate that from the A value to be worth about 0.7 kilocalories per mole. However, now, if we were to do the Newman projection, now these groups are staggered. So by doing the addition to cyclohexanone, we relieve 4 kilocalories per mole of eclipsed destabilization, and we only introduce around 1 kilocalorie per mole of 1,3 diaxial repulsion or steric hindrance. And so you can see those offsetting factors. If you have the idea that a regular carbonyl should be have an equilibrium constant around 10 to the minus 3, we're 2 orders of magnitude greater than that in terms of equilibrium constant. Overall, if we estimate that if we estimate the difference in free energy between these two states as being around minus 3 kilocalories per mole. Remember that at room temperature, 1.4 kilocalories per mole is a factor of 10 in equilibrium constant. So it sort of makes sense that if the delta G is 3, that the cyclohexanone should be 100 times more reactive than the ketone. And that's, again, because of relief of an eclipsed interaction. And this is true not only for the hydrate, but for other kinds of carbonyl additions to cyclohexanone. Okay, any questions? I mean, it's not like you're ever going to do a carbonyl hydration reaction, but physical organic chemists aren't so much about useful reactions, but rather reactions that let us learn something about the physics and the sterics and stereoelectronics of the molecules that we'll be dealing with. Right. So I could show you a similar pattern for cyanohydrin formation. That's adding cyanide to CN minus to the carbonyl in the presence of some acid. I won't bother because it's basically similar. Let's talk Grignard just a little bit, and this is going to be a lot of physical organic chemistry is also debunking popular understandings of the way reactions work. So what we'll show you here is that it tends to be a little bit more complicated. The typical way we think of the Grignard reagent is that it's basically R minus, Mg2 plus, and Br minus. And we deal with the Grignard nucleophile as though it were basically an anion. But that's not actually how it is, and there is some substantial covalent character between the carbon and the magnesium. The typical expected mechanism, the way you would typically draw a Grignard mechanism, and it's not wrong, is you would take the electrons in the bond between carbon and the magnesium. Let's just be very clear. They would leave for magnesium and they would attack the carbonyl carbon, and you'd get a tetrahedral intermediate. Typically we draw that like this, and we ignore the counter ions. Some people will say, oh well, probably The oxygen then associates with the magnesium, and there you are until aqueous workup, whereupon you get the alcohol. All right? And that's fine, but there's evidence that it can be more complicated than that. So, here's an alternative mechanism that involves something that's called single electron transfer. And when I hear those words, my eyes glaze over, and I'm like, I don't really care. And you may not either, and that's that's fine. But I thought it was interesting enough that it may be, and surprising enough to me that it maybe deserved us to just mention it. So, a single electron transfer mechanism would involve one electron going on to the carbon and another electron being transferred to the carbonyl compound. And it's sort of difficult to push arrows for single electron transfer. We're literally donating the other electron in that bond to the carbonyl. But if we drew something like this, it looks like we've got too many valence electrons. So perhaps the better way of thinking of this is, after the addition, you have a negatively charged radical. This is sometimes called, well, often called a radical anion. And then your other product is just R. And it can also be called a ketyl radical, although I haven't ever heard that term except in this textbook. And then, of course, you have MgBr plus somewhere. And then it's thought in a subsequent step, you do radical coupling, and that generates your expected product, etc. What is the evidence for this? Well, you might expect to see, whenever you have a radical species, you might expect to see some radical coupling. So if you observe any of that, where you make a new bond between R, or if you observe any of this, where you make a new bond between ketyl anions, that would be evidence for single electron transfer. And that is sometimes, if I'm remembering right from your text, sometimes observed. So all I'm saying is continue to draw the Grignard mechanism like this, but be prepared for weirdness. Yeah?
So what initiates the single electron transfer? Like, why does it just lose?
Yeah, what initiates a single electron transfer? Short answer is I don't know. A little more complicated answer is this is a reduction reaction, so it must have to do with oxidation reduction potentials. And it must be, if this were to happen, you would think that somehow there should be a reduction potential associated with giving one electron to that molecule, and an oxidation potential associated with going from basically an anion to a radical, and those in that case have to match in order to make it happen. I think I'm just making stuff up. Anybody know anything better? You inorganic folks that have taken that class, do you ever talk about single electron transfer? No? Okay. Yeah. I mean, it's in OChem we're used to arrows which indicate that nuclei move with electrons. Single electron transfers like hop. And I'm not sure if that's the best way to think of it or not. Also, there is some evidence that the process can be more than bimolecular. So this was wild when I saw it, and I thought maybe it's worth thinking about. Grignard reagents, you can use Br or Cl as counterions there, doesn't really matter. So there's some evidence that it requires two equivalents of Grignard reagent to attack the carbonyl. That at this stage, the oxygen chelates to the magnesium, and then this R group goes to that magnesium. And if you follow that through, what that does is it prevents you from ever having a negatively charged tetrahedral intermediate. And only one equivalent of the Grignard reagent is consumed. All right, so a couple different complexities. If you were doing kinetic experiments and you discovered that the rate of the reaction required, the rate law was bimolecular in Grignard reagent, you'd have an idea as to why.
Is it?
Have I ever done a kinetic experiment on a Grignard reagent? No. There's, I don't know what the specific example is in the text. I believe your text just indicates that there's some evidence for this sometimes. Okay, so I sat in on my colleague Josh Anderson's biochemistry 482 class, and he said, in molecular biology, you just need to get it out of your head that effects are going to be 100%, all or nothing. And in chemistry, well, that's a form of chemistry. In OChem, we like hard and fast rules, but only when we're starting to teach you about it. We sort of lure you in with that simplicity and elegance, and then you come to discover that the real world is more complicated than that. So I told you that physical organic chemists like to debunk conventional wisdom. All right, so I'm just going to put sometimes. And we don't know whether that's sometimes, or Cookie Monster sometimes. So you guys probably don't know Sesame Street. Maybe you didn't grow up with that, but you've probably heard of the Cookie Monster. Anyway, in my day, Cookie Monster was a glutton. He would just eat cookies like crazy. Nom, 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 nom. And more recently, he said that cookies are a sometimes food, and we need to eat other things than carrots. But Cookie Monster, yeah, we don't know whether it's really sometimes or sometimes like all the time, in the way that cookies are a sometimes food. All right, sorry. Let's talk briefly about let's see. I don't think I want to talk about lithium aluminum hydride reductions. I will just say that organolithium reagents and lithium aluminum hydride, with lithium there can be a lot of ion pairing. Lithium likes to bond with oxygen, and there's evidence that the organolithium reagent that looks like, that we draw like this, is actually a much larger thing, right? And perhaps more than that. You can do actually lithium NMR to try to tease out some of those issues, but we won't worry about that. Organic chemists prefer to think of things as simply as possible. Okay, just running through all the various issues. Let's talk about carbonyl chemistry, diastereoselectivity. So imagine you have some carbonyl compound and you have a stereocenter at the alpha carbon, at which there is a large group, a medium group, and a small group. And the question is, if I have a nucleophile attack, do I get, there's a possibility of two different diastereomers, right? Because this ketone has two diastereotopic faces. It's got a ray face and a psi face. You can get this diastereomer, or you can get the alternative, in which, will show the nucleophile here and the OH group there. And so the idea is which is the major diastereomer. Do you see how those are diastereomers? Yeah, okay. The stereocenter here isn't changing. So people have tried to rationalize and predict this, and there is the best, or at least most sophisticated model that seems to work a lot of the time is called the Felkin-On model. Physical organic chemists like to have things, and organic chemists in general like named reactions. It's like how you show, it's like name dropping, but with molecules and models instead of people. So anyway, the idea is let's take the carbonyl compound and let's look at it from the perspective of this bond between carbonyl carbon and alpha carbon. All right, so if we do that, in our carbon in the front, the carbonyl oxygen's going up, the R group is going down, and then in the back, we have the small, the large, and the medium group, okay? And we can ask, as I've currently drawn it, we have the small group here, we have the large group here, and we've got the medium group there. It's thought that the best conformation for that stereocenter is to put the largest group here. That is perpendicular to the carbonyl. And with the configuration of the stereocenter that we have, that would put the small group here and then the medium group there. Of course, we could rotate around the bond between carbonyl carbon and alpha carbon such that the large group was projected here, and then the small group would be here, and the medium group would be there. Take a minute and look at that and make sure that you've convinced yourselves those are the same molecule. You just rotated around the carbonyl carbon to alpha carbon bond.
Would the S be on the bottom on the left?
The way we've drawn it, the S is eclipsed with the carbonyl. You know what? I think I got mixed up. So if I'm looking at it from this direction, the way I've drawn it there, small group should be eclipsed with the carbonyl. The large group would be, on my right, and the medium group here, right? Okay. So I can draw one of two possible structures. We can draw the large group here, in which case medium and small. Or we can draw a large group here, small and medium. Okay, why is that the best conformation? You can think of it in terms of steric interactions as the nucleophile attacks. It makes sense to move the largest group out of the way, all right? Another explanation that Paul Savage told me years ago when I took this class was that you've got the pi star associated with the carbonyl, and you want the large group to line up with the pi star to facilitate donor-acceptor hyperconjugation interactions. Let's see, I'll say the if in just a little bit. Now, you can see then that the left-hand side face and the right-hand side face of the carbonyl are different. If the nucleophile approaches the left-hand side face, it's going to see small group up top, medium group on the bottom, opposite if it approaches from the other side. Now, here's where that Bürgi-Dunitz angle becomes important. The addition, because you need to know the trajectory at which the nucleophile attacks the carbonyl. If it came in from this direction, you might think, okay, well, that approach from that side is good because we encountered the small group in this trajectory, but the medium group in that trajectory. But that's not how carbonyl addition happens. The Bürgi-Dunitz angle says, whoops, we're going to erase everything, says that the incoming trajectory of the nucleophile needs to be at about 105 degrees. I did that on the wrong side, didn't I? So that incoming trajectory of about 105 degrees, whereby the nucleophile approaches the carbonyl carbon, that's going to bring it basically eclipsed with the medium group, and then if we do the same here, the nucleophile can approach over the small group. And the idea is that this is favored. All right? So, going back to and it's favored because of sterics. Okay, so if we go back to our options up above, the one on the left is what we would see if the nucleophile added from above, and so that would be diastereomer 1. This is diastereomer 2, where the nucleophile adds from below, and this is the one that's preferred, and that's the major diastereomer. Now, of course, you might imagine that diastereoselectivity is going to depend on the relative size of these groups, and you can think of lots of situations where it wouldn't be very good. In particular, if one of the, let's just replace one of the groups on that stereocenter. Let's make it, say, an amino group. So, sorry, here's a small group. Here's some other group. I'm not sure what we're going to call them. We'll just call them R1 and R2. I meant to do a dash there and a wedge here. And let's just suppose this is some amino group, or too many R's here. I don't want to be specific on what that amino group is attached to. So I don't.
Use L.
L, okay, sure. L for ligand, which is kind of, okay, whatever. Or, oh, I know, P for protecting group. Or maybe pH. So it's an amide or some kind of carbamate or something. Okay, whatever. The point is you have an electronegative atom attached to the alpha carbon, and that's going to change the electronics just a little bit. Let's just sort of redraw these things from our perspective. The nitrogen, as we've drawn it, would be here. The R1 group would be here, and the R2 group would be here. And it turns out that the best conformation for attack is the one where, independent of size, where the electronegative heteroatom is at this sort of perpendicular position. And the reason for that is that it's thought that as the nucleophile attacks, and this has got, nucleophiles have extra electron density, it can, as it's approaching, overlap with the sigma star orbital, the carbon-nitrogen sigma star orbital, which, because this is an electronegative heteroatom, should be lower in energy than any of the other sigma star antibonding orbitals. And as the nucleophile aligns with that orbital coming in, it's a stabilizing interaction.
So are we assuming that this large group is so big that it's like deterring any entry from the other face?
Are we assuming that the larger group is so big it's deterring any entry from the other face? Sure. And you could imagine that the diastereoselectivity might not be that good.
Because I keep looking at it like, why don't we just come in between the L and the R right there?
That's right.
It's a nice big gap.
That's right. And the L, the M, and the S don't really capture, the space filling issues. And I should have looked up a specific example, but this is the best I did. So, right. I feel like this is just sort of a random fun fact day. I think for alpha beta unsaturated carbonyl compounds, you have the option to do 1,2 nucleophilic addition where the nucleophile attacks the carbonyl carbon, or you have the option to do 1,4 addition where the nucleophile attacks the beta carbon. And the rationale for first of all, why do they call it 1,2 versus 1,4 addition? Here, the carbonyl attacks position 2, and then the hydrogen goes on position 1. Why isn't this called 3,4 addition? And the answer is it's thought that maybe the enol is the intermediate first, and then it tautomerizes to the ketone. The reason this can occur, of course, is that for this conjugated system, the LUMO is delocalized across all of the molecules. So we're just looking at one. Is that right? Yes. We're just looking at one face of the LUMO. This is the pi3 orbital of a conjugated 4-atom system. But LUMO is on the carbonyl carbon and it's on the beta carbon, and so we can attack at either of those places. In introductory OChem, I think you were told that that the Grignard reagents and the organolithium reagents prefer 1,2 addition. This is true especially for hard nucleophiles. Hard nucleophiles, remember, are those that are typically small and have negative charges on them. They are usually electronegative elements, and they're motivated mostly by electrostatic attraction, Coulombic attraction between negative charge and positive charge. And so it would make sense that the hard nucleophiles would attack here because that's closer to the carbonyl, so there should be more partial positive charge on that carbon. In contrast, the soft nucleophiles prefer 1,4 addition because instead of electrostatic attraction, soft nucleophiles tend to have diffuse and spread out charges, and so the thing that allows them to attack is orbital overlap. And so molecules that are close in energy to the LUMO of the alpha beta unsaturated carbonyl compound will tend to attack at carbon 4. So you're looking for soft nucleophiles like thiolates. This is important in chemical biology and biochemistry. You can selectively modify cysteines with alpha beta unsaturated carbonyl compounds. Enolates given the choice, would prefer to do the conjugate addition. Cuprates as well. All of these are sort of softer nucleophiles where orbital overlap is more important. And I think the rationale is that the LUMO coefficient, orbital coefficient, is higher on the beta carbon. All right, so that's just if in case you missed that in undergrad, or in your introductory OChem class, the reason organolithiums and Grignards prefer 1,2 addition is because they're hard nucleophiles, and that's where a lot of partial positive charge is. In contrast, the reason soft nucleophiles prefer to attack at the beta carbon is because that's where most of the LUMO is. All right, let's see. So thoroughly debunked carbonyl chemistry. What we'll do in the last couple minutes is we'll talk about basically intramolecular addition reactions and something called Baldwin's rules. And these come up occasionally. You could try to memorize them, but I think probably don't. Just look them up. There are a couple of factors that you should consider when thinking about intramolecular addition reactions. The first is the size of the ring that you're going to form. So 3, 4, 5, 6, 7. Baldwin's rules relate to intermolecular addition reactions that are fast versus slow, and it's due to orbital considerations, where the LUMO is, and it's also due to geometry and whether the nucleophile can reach the orbital that it's attacking. And ring geometry only tends to matter within this sort of constraint. Beyond that, larger rings, the nucleophile has way more freedom and can basically attack where it wants to. The second issue to consider is hybridization of the atom being attacked. I realize none of this makes sense because I haven't given you an example yet, and that's fine. We just need to sort of pay attention. sp3, that would be like in a substitution reaction, sp2 or sp. Only in the Baldwin rules, they couldn't stick with sp2, sp3, and sp. Instead, they call if the atom is sp3 hybridized that's being attacked, we call that, we classify that as a tet situation for tetrahedral. If it's sp2, we call it trig for trigonal planar, and if it's sp, we call that dig for, I don't know, diagonally or something. Probably di for 2, and then they kept the G from trig. I have no idea. Diagonal planar, is that? So if you think about the hybridization of the atoms that are being attacked, that does influence the LUMO geometry at that atom. For example, if the atom's sp3 hybridized, chances are you're attacking a sigma star, and chances are that's 180 degrees behind the bond that's breaking. So your nucleophile has to be able to get there. If it's sp2 or sp3 hybridized, sp2 or sp hybridized, likely the LUMO is a pi star, and you're going to want to approach that from the Bürgi-Dunitz angle, which is around 105. Okay. So what that means is depending on the ring size and the placement of the LUMO, your nucleophile in your intramolecular reaction has to be able to get to the electrophile. And finally, the last factor, which is annoying, is called exo versus endo. And that has to do with when you do the attack, is the atom that picks up the charge. I'll just explain that next time because it's confusing. It's not as bad when you see an example, but it's hard to explain without an example. So we'll just wait for that till after the break. If you're dying to know, just look it up. And have a very happy Thanksgiving. Please be safe. Please do not do stupid things. Do not get injured. Wear your seatbelts when you're driving. What else? Get plenty of sleep.